what is digital design verification? So if you, after you finish this course, you know all about Verilog and stuff. If you went out into industry, um, your first job, you would unlikely be designing analog circuits. You would mostly be doing verification. Let's get this comment thing going. Verification. And verification is basically running tests, creating test benches to make sure that the designs work correctly under all situations. And typically 70 or even more percent of the design effort goes into verification. That means like if there's 10 engineers working on a digital project, 7 of the 10 are just making sure the design works correctly. The other 3 are designing it. It doesn't exactly work like that way. I'll explain that later on. But basically 70% of the effort goes into verification, and 30 or less, 70 or more goes into verification, and 30 or less goes into the actual design itself. And it's interesting to explain what a typical day is for a digital verification engineer. So assuming you were going into office, you would get into the office. The first thing you do in the morning is overnight, you ran all kinds of tests, and you would spend the first hour or two just looking at the logs from your tests from the night before to make sure that if there were errors, to find out what the errors are, identify them. So you spend the first couple hours doing that, looking at logs. Then you spend most of the day writing little tests, setting up tests that are going to run at night, and doing little scripts to help run the test and figure out where the holes are in your test and so on. And then before you leave, you start up a whole sequence of tests that are going to run overnight. And typically there's a farm with literally hundreds of processors or even thousands in some cases that run these tests all night. And we'll explain why this, but that's the typical scenario. And the next day you go in, you do the exact same thing. You look at the logs, figure out what the tests are, what things went wrong, what went right, how can I make new, better tests, and you run those tests the next night. So that's the life of a verification engineer. I'll explain what verification is. But anyway, typically what happens is you have a design that's under verification, DUV, that's the acronym for it. And then there's this verification environment around it that applies tests and sees the results of the test. And unlike what you've been doing so far, like in all your labs, typically your verification environment was, okay, you wrote a test bench, and the test bench applied some signals to your waveform, to your circuit that you were designing. And then the output was the waveforms. You just looked at the waveforms and said, oh yeah, that's doing kind of what I wanted to do. It counts, or it loads, or whatever you were wanting the circuit to do. That's okay for like a simple little design that you're doing for a lab in this course. But in real life, where you have, literally billions of gates in here, that doesn't work. The whole system breaks down. So these verification environments we're going to explain later on are pretty complicated. There's a lot to them, how we build them and how they work. And we don't have time to go through all of it, but we've got a lecture here or two to talk about some of this verification. But anyways, verification is super important. We could have a whole course on verification. Unfortunately, we don't have time for that. The next thing I'm going to explain the difference between verification and testing. And there's actually 3 words people use it commonly and sometimes interchangeably. And one is verification, one is testing, and one is validation. I'm going to stick to the 2 main things. I'm going to call them verification and testing. And the distinction I'm going to make is, so let's say you're given a spec here, which is in yellow, and you're designing something and you generate a net list, either a gate level or RTL. Let's say it's a gate level net list. And then you don't like, you do some simulation on that, you don't like it, then you check it, you don't like it. That process is verification. You go back and you check the spec and you change the design. So this is verification. It's basically this loop before you get a final net list that's going to generate the chip to be sent out, okay? So you're happy with this net list. You send it to the company that fabricates it. They build a chip for you. This is a real silicon chip and a package. And then it comes back and you test it. and you say, oh, you know what, it works like 100%, we're going to sell this, or it says, oh, somebody busted this, or this doesn't reset right, or something, and you say, oh, this net list is no good. So you might end up going back here again, redesigning it and whatnot, and verifying it. But the main point here is verification is stuff that happens before the chip gets sent out for fabrication. Testing is stuff that happens after you have real hardware that you're making sure that it works correctly. Okay. So testing terms of design is fabricated properly. Verification terms of design meets the functional intent of the specifications. And then sometimes they use validation terms if the product meets the customer's wishes. So anyway, I'm not going to use this much. We're just going to mainly talk about verification and testing, just to keep things simple. Any questions about that? Okay, it turns out there's two main categories of verification. There are tools that will formally look at your circuit and say, yes, this is correct by construction or not. And then there's the more common, which we've been using, which is assertion-based verification. So basically what you're doing is you're asserting some signals, you're running some simulation, you're seeing that, yeah, the circuit is working correctly. By far, assertion-based verification is what most people use, okay? They're doing simulations with signals being applied and looking at the outputs, either visually or automated. Formal verification is not used very much. It's not very widely, it doesn't work on all kinds of things. The one place that it actually is used is to find equivalency between netlists. So for instance, if you have RTL, you generate a gate level netlist, then you do a place and route, you generate another netlist. We often use an automated tool that does formal verification that, yeah, these netlists match each other. But that's kind of like the only place it's really used. Okay. What is a verification engineer? I kind of talked about what the day is for in the life of a verification engineer, but basically these are kind of the main tasks. They check to make sure that the specifications are complete and consistent. They develop a plan, so how they're going to verify the chip that they're doing. And it'll include, and we'll talk more about this, some directed tests, some random testing, some test checkers. So all these things have to be part of the plan. They verify that the implementation meets the specifications. Things like, does it have sufficient code coverage? Are there no bugs in the last certain period of time? It's impossible to verify that you 100% coverage, but usually there's some metrics of what the code coverage is, how many bugs are found in a certain period of time. But anyway, they verify the design. And here's an interesting thing I highlighted in red here is different designers. So it's important that whoever's doing the verification is not the same person that did the design. And this comes back to our Heisenberg principle, right? If I design the circuit and then I tried to verify it, well, I know all the ins and outs of the circuit, I would just generally not be good at verifying my own circuits because I wouldn't try things that I already thought of, right? So it's important that the verification engineers are different than designers. Now, that doesn't mean all people are either designers or verification engineers. Usually what happens is you design a part, but somebody else might design another part, and then you switch roles. If I designed a part and you designed a part, well, I'll verify your part and you'll verify my part. So when I said, 70% of the effort, that doesn't mean 70% of the people are just doing verification. That just means that, you do a lot, everybody does some design, but you do more verification than you do design. And when you first start, you might do a lot of verification and just a little bit of design. And as you get more experience, you might do a higher percentage of design to verification. But generally what's happening is people are switching roles all the time, doing some design and some verification. But it's important that, you don't try to do this all by yourself. So by having different designers, you're less likely to misinterpret the specs. And here's another interesting, it helps find verification environment bugs. So this environment that you're using to verify this design, you can have bugs in it as well, right? These test benches. And so let's say you write some of this verification environment, but somebody that was doing the design says it comes up and says, okay, I'm going to use this to verify my chip. And they say, oh, well, you messed up this thing in the verification environment. So you're kind of cross-checking each other both ways. The designer's checking the verification environment, and the verification engineers checking the design. So it's kind of a good situation. Anyway, that's our Heisenberg principle, right? Both ways. The next thing we're going to talk about is system Verilog. So we talked a little bit about this through the course. So there was different versions of Verilog, and then eventually the most recent one is called System Verilog. And System Verilog has all the functionality that Verilog had for design, but it also has a bunch of new things that were added to make generating test benches, complex test benches or verification environments easier. So as designs outgrew verification abilities of Verilog and VHDL, the Harvard Design verification languages were developed. 2005, the EDA companies came together and they formed System Verilog. 2009, the latest version of Verilog was merged with System Verilog to create the language of both design and verification. Yeah, so System Verilog since around 2009. So it's been around for quite a while, and it's become very common. And I would say, historically, people did design with Verilog or VHDL, but I would say majority now have moved to System Verilog. If you look in industry, most people are using System Verilog. System Verilog uses constrained random tests that use functional coverage to measure progress and direct the verification. We'll explain what that meant, but this is like kind of a key attribute that is built into System Verilog. It helps us to verify our designs much better. It also allows the construction of reliable, repeatable verification environments using both internal and external VIP. So what's VIP? We've learned what IP is, right? IP is intellectual property. That's like, oh, you've been using IP in the lab all the time. You got Xilinx gave you a PLL that you used. Xilinx gave you some counters, IP used. VIP means verification IP, because sometimes you have a design, like say you have a USB master part of your chip that you IP you want to put. How do I make sure it's working right with all my other stuff? I need to verify it. Well, there's companies that say, well, here's the verification environment. Here's the test benches and the tests you need to run to make sure that your block is working okay. So people will sell you not only IP, they'll sell you VIP. So they'll sell you both of those things. And we call that verification intellectual property. And often you buy this and you can use it in multiple projects. So what are the characteristics of a hardware verification language like System Verilog? It has constrained random stimulus generation. We'll talk about that in a minute, why that's super important. It has high-level constructs like object-oriented programming, transaction-level modeling. You can have multiple processes running in parallel. You can split processes, and you can multi-thread and have inter-processor communication. You can support Verilog's 4 state values, 0, 1, X, and Z, and you have tight integration with the simulator control of the design. So all those things are important. The goal is to create test benches at a higher level of abstraction so that you can use the same test bench for many kinds of tests. You want to reuse your verification environment from one project to the next. You want interoperability between the blocks. You want to use VIP as much as you can, because big companies with if you're doing a complex design, you can't afford to generate all the IP or all the VIP yourself. So you want to be able to use that. So System Verilog supports that. You want a separate stimulus generation and stimulus delivery. We'll explain why that is in a minute. You want to use the best practice of all companies, and then sort of the hidden agenda is the EDA companies. There's 2 major EDA companies, which are Synopsys, Mentor, and Cadence. And they want to sell you this VIP and IP. So their hidden agenda is to sell you more of this. So they love System Verilog. That's why they all got together and agreed to, okay, let's use this standard so that we can all sell products to companies, other companies. Okay, before we get to this stuff, the other thing that's important that you'll run into out in industry is In addition to System Verilog, people have come up with a design methodology, and there's what's called the Universal Verification Methodology, or UVM. You'll hear this term all the time. And it's basically, in addition to System Verilog, it includes a bunch of other things like libraries of classes, sort of a mechanisms, or we call it a factory for constructing the objects in those classes, utilities for managing log files, transaction level modeling and communication between components is sort of included in it, and macros for semi-automatic generation of the verification code. So all of that's within UVM. And UVM sort of emerged out of a bunch of different previous variants of these methodologies. There was AVM, VVM, URM, OVM. Eventually in 2011, again, Cadence, Mentor, and Synopsys came together and they said, not only are we going to do System Verilog, but we're going to use UVM. So this is on top of System Verilog for people to build their verification environments. And UVM has all this additional stuff in addition to System Verilog so that you can do verification. And this has become a de facto standard. It's been around since 2011, but any big company you go to will almost 100% guarantee they'll be using the UVM environment for doing verification. Okay, so that's a lot of information, but let's get back to a little bit of the nitty gritty of why we wanted this. So this is called directed testing. This is what you've been doing in the lab. So basically what happens in the lab is, let's say you're building your egg timer circuit. You say, okay, I need a counter. So you design a counter and you test the counter. That's the first step. Then you say, oh, I need a 7-segment display driver. Oh, so you design the 7-segment driver and you verify that works. And then you say, oh, I need something to keep divide down and generate a 1-second clock. So you design a divider for the 1-second clock. Then you test that. Then you go on and on. You build the blocks, you test the blocks. Eventually, you're going to get through all the blocks, get them all verified, and you're 100% done. You verified that the whole egg timer works together. That's called directed testing. You're just going through the blocks, testing them individually, adding them all together, and then testing all of them and making sure it works. It's an incremental approach where tests are written for each set of features and verified sequentially, okay? Well, let me just back up. That was good in the past when we had simple design. It turns out when you have a really complex design with a lot of blocks that work together, this becomes unmanageable. It just takes too long. Like getting to this endpoint, instead of taking a few months where you have design time, this takes years. Like, when you've got billions of transistors, the time kept getting longer and longer and longer to get to this point. And so they had to give up on it. It was just too hard to do. So first thing is, people realize, well, instead of me writing all the tests, can I come up with a way to automatically? Remember I told you, oh, what's my golden rule? Automate them before they automate you, right? So this is kind of the scenario. People said, we got to come up with some automated way to verify that these circuits are working. And one of the key things to that is to do random testing. And the idea of random testing is, oh, you know what? Like, let me give you an example. Let's say I have a counter. And this is a loadable counter. And this is my output. And let's say this is an 8-bit counter, okay? So I can load a value. So there's a clock, there's a load signal, and there's a load data, and there's the outputs, right? And if you were verifying this counter, you would say, okay, let's load the signal. I'll load it with a code of 10. And then it was X. I load it with a code of 10. And then here's my clock. I let the clock run a long time. And I check the output at a couple of times. I say, oh, okay. Every clock cycle it's counting up, right? So it starts off at 10, it goes to 11, da 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 da. Eventually it goes to, this case, 255, and then it goes back around to 0 and so on. and it counts them all. And then later on, you say, okay, I'm going to load it with a new code. I want to make sure this loading is work. So I loaded 10. Let me try to load it with 220 or something. I don't know. And then I run a bunch of more clocks and I look at a bunch of these outputs that are changing. And you do all this manually. You look at the waveform, and you would try to come up with a sequence of, maybe I load it with 0 first, and then I load it with 255, and then I try something in the middle, and then I run a certain number of clocks, and you look at the waveforms. Well, that's takes a lot of time. You run these, and you're manually looking at these things. So that's very time consuming, and actually it's error prone as well. So what we really want is something that says, oh, okay, let's say we got a random number of clocks. We're going to load random values in, and we're going to have some expected counts. We're going to write a program that says after this many clocks and this random loading, and I expect this count, and I'm going to do all that automatically. So by randomly generating signals, looking at the results that automate the readout of those, I can basically, instead of me doing it manually, I let it run all night long with all kinds of random inputs here, run it for hundreds, thousands, millions of test cases, different, there's not a million test cases there, but maybe I try a huge number of the possible different loads and runnings for certain amounts of time to see that everything works. So that's the idea. Don't do these things manually. Let some automated thing do it. And key to that is randomizing that. So randomized tests use a randomized stimulus to find bugs you never anticipated. It requires an automated results prediction, which is called a scoreboard. So that in this case, the count, we need to have something that says, oh yeah, if you load this value in this many clocks, this is what my expected count is. So you need some kind of golden design, which could be a behavioral model or an FPGA to measure it. And in addition to these random tests, you wanted to constrain them, right? So for instance, if you're loading in the count, well, you can't, there's no sense of loading in counts that are greater than 255, right? So there's some constraints about how many counts you would run and how many clock signals. You don't, if it's an 8-bit counter, I don't need to run 2 million clock signals. I want to constrain the number of clock signals to something that's maybe, 500 or 255 or something like that. So it's randomizing the tests, constraining them so they don't take forever, and I can cover as much of the circuit operation as possible. So that's the idea. That's a key thing about verification environments and System Verilog. It's you can use constrained or random testing. We're going to layer test bench breaks the problem into manageable pieces. We're going to see what that looks like. Transactors provide useful patterns for building these pieces. So you could have a transactor that did the loading and the clocking. You could just, it would do that automatically. You just tell the transactor, randomize these 8-bit values and these number of clocks, and the transactor would do that. With careful planning, you can create test bench infrastructure that can be shared by all tests. It provides hooks where tests can shape stimulus and inject disturbances, i.e. insert bugs, and see if they're detected at the outputs or internally. These are often called assertions, being able to assert to see if there's any errors inside your chip. Code for specific attempts is kept in separate from the actual test benches. So this picture below shows the idea of this whole constrained random testing. So originally we were doing directed testing, and we said this was the scenario. We took each block, we verified it, and then we added one feature after another. Eventually we got to the end. The idea with constrained random testing is, well, we have to build up this automated environment. So it takes quite a bit of time here before we start running any tests, okay? So this initial creation of the environment is a lot of work, okay? And so it's got to be a big enough project that it's worth putting all this effort into. But once you have this and you're running all these random tests, the idea is that you're going to quickly get to this 100% coverage long before if you did the directed testing when it's a super complicated thing, because you can use the power of this randomized environment to run millions, billions of tests over many, many days. In fact, this testing begins early on in the design. The verification environment is set earlier you set it up, the better. You start verifying your design like, maybe a third of the way into the project or even less, and it runs for many months. Even after you've sent the chip out, people keep running these verification tests to see if they can find bugs because it's all automated. It doesn't cost anything. You just run it and check the logs, right? So that's the whole idea is that, we get to this endpoint much faster. We have a complicated environment, but it randomizes and creates a lot of the tests for us. It does a lot of the work automatically. And this sort of just shows this kind of is another way of looking at what I described the day of a verification engineer. So basically, we have a design, uh, and you during the day, the verification engineer is running directed tests, and they get run on the design, and they come back and they're kind of running all these little tests during the day, finding any little bugs or holes or things that they want to limit the constraints on or so on. And then at night they add constraints and they run these constrained random tests, and they run many different runs, randomized with many different seeds. And then at the end of the day, they come in, they look at the logs, and they see, okay, what kind of bugs did I have? What kind of errors is? What kind of coverage do I have? And from that, they spend the rest of the day. So this is the during the daytime, they're going around this loop, and at night, it can even happen during the day, but mostly at night, all this stuff is running. So constrained random testing, although you want the simulator to generate stimulus, you don't want totally random values. For example, if you had a 32-bit opcode for an ALU, the processor would be constrained to doing the functions of the ALU, which might be add, subtract, store, a few other things, but it doesn't do 2 to the 32 different types of operations. So you don't want totally random. They have to be constrained to find the problems. And as you go verification develops, you want to try to find new bugs. You constrain them in different ways. Randomizing data fields for design is easy, but typically gives low payback. Random testing is typically good for data paths and control path errors. But generally, you want to think broadly. You want to randomize the device configuration, the environment configuration, the input data, protocol exceptions, errors and violations, delays. All these things get randomized as much as you can to get as much coverage of different kinds of bugs. Yeah, and this is just showing if you